Hey, it's me, Mr. Patterson, here with you to go through Core Book, Section 10D, Theoretical Probability. Fair warning, this lesson will be a little bit longer than the previous ones. We're going to talk about how to find theoretical probabilities from a variety of different perspectives. We're going to talk about how to represent the probabilities in different ways that'll help us find probabilities a little bit easier. And when to kind of know when to use which representation. So first of all, what is theoretical probability? We spent some time looking at experimental probability. Now we're looking at theoretical probability. And basically, what we're talking about is using math in order to find out how likely certain outcomes are. That's what theoretical probability is. If we look at our example over on the right, we see a spinner that is made from a regular octagon. Therefore, all of the outcomes are equally likely. So therefore, the probability of any one of those outcomes is just 1 over n, and in this case being 8. Little note about probability notation, something that I am very, very critical of, making sure that you follow this format here. We put a P on the outside, and on the inside we put whatever the event is. So the probability of A is how we read that, and it's just the number of outcomes that correspond to A divided by the total number of outcomes in the sample space, or n of A over n of U, U being the sample space. So let's get to some examples. In this example, we have a basket that has 3 green, 4 yellow, and 5 blue tickets. If I'm looking for the probability of a green ticket, using the formula we saw in the previous slide, how many green tickets are there? There are 3. How many total tickets are there? There are 12, therefore it's 3/12 or a quarter. Part B says a green or a yellow ticket. Green or a yellow. There are 3 green and 4 yellow, therefore there are 7 green or yellow tickets. Out of 12, 7/12. C says orange ticket. Well, there are no orange tickets, therefore the probability of orange is 0. Green, yellow, or blue. Well, those are the 3 colors that we have, therefore it is all of them, 12 out of 12 or 1. We're going to look at example 7 here. In this case, we're just rolling a single-sided die and determining the chance of these different outcomes. Probably take a pause to the video here and see if you can find these yourself before you watch through. So we know the sample space is all integers 1 through 6 inclusive, and they're all equally likely. So we're just going to say the probability of getting a 6 is 1 out of 6. Probability of not getting a 6, well, there are 5 outcomes that are not 6s, so it's just 5 out of 6. 1 or a 2, there are 2 outcomes that are 1s and 2s out of a total of 6, 2, 6, or 1/3. Not getting a 1 or 2, well, that just means it could be a 3, 4, 5, or 6. Those are 4 outcomes, 4 out of 6, or 2/3. Complementary rule. So while I could have on the previous slide, instead of looking at example D and saying that it is going to be the probability of a 3, 4, 5, or 6, I could have just done 1 minus the probability that it's a 1 or a 2, because those are complementary events. In our notation, we see that the probability of A plus the probability of not A is equal to 1, because the event A either happens or it does not. So the probability of an event plus its complement has to be 1. Let's take a look at this example here. It says, first of all, use a 2-dimensional grid to illustrate the sample space of tossing a coin and rolling a die. So tossing a coin could be heads or tails. Rolling a die could be anywhere between 1 through 6, inclusive integers there. So here's our 2-dimensional grid. Now, if I'm looking for the probability of tossing a head, okay, tossing a head, there are 1, 2, 3, 4, 5, 6 outcomes that correspond to tossing a head out of a total of 12 total outcomes. Therefore, the probability of tossing a head is 6 out of 12 or a half. B says tossing a tail and rolling a 5. Okay, so it has to be a tail and it has to be a 5. There's only 1 dot on the 2-dimensional grid that satisfies that. Therefore, B is just 1/12. But when I look at C, tossing a tail or rolling a 5, well, there are 6 instances of tails. There are 2 instances of looking for a 5, but one of those is a tail and a 5. So there's actually only a total of 7 outcomes that are tails or rolling a 5. That's why C is 7 out of 12. Because in probability, we take a tail or a 5 to mean a tail or a 5 or both. And that's an important distinction to make sure you understand when you're finding or probabilities, as what these are referred to as. Example 9, it says display the possible results when 2 dice are rolled and the scores are added together. Then find the probability that the sum is a 7. So this is something that we use often in probability. Looking at those different outcomes, we see die 1 on the horizontal axis, we see die 2 on the vertical axis, and all of these numbers here in the middle represent the sums of those different outcomes. For instance, this 6 right here means that I got a 2 on die 1 and a 4 on die 2. Notice that's different than getting a 2 on die 2 and a 4 on die 1. Okay, sorry, 4 on that one, right here, that's 6, all right? The sum is the same, but they're considered separate outcomes, all right? So when we're talking about the probability of getting a sum of 7, how many times did I get that 7? I got it 6 times out of a total of 36, therefore it's 6 out of 36, or 1/6 is what it reduces to. Example 10, talking about Venn diagrams. It says in this Venn diagram, the universal set U is the children in a class, and each dot represents a student. Event B is that the student has blue eyes, and find the probability that a randomly selected child has blue eyes. Okay, so if I look at it, I see that there are 8 dots inside event B, and there are 15 dots not in event B, giving us a total of, what is it, 23 total students here. So I have 8 in, 15 out. Therefore, the n of u, the number of elements in the sample space, is 23, and n of b, the number of elements in event B, is 8. Now we have enough information to answer the question more easily. So the probability that they have blue eyes, okay? So there are 8 with blue eyes out of 23. So therefore, the probability of blue eyes is 8 out of 23. Does not have blue eyes. Well, I could just take those 15 out of the 23 and say, boom, that's probably that they don't have blue eyes. Or I could come in and say, it's just 1 minus probably that they do have blue eyes. So I could say it's 15 out of 23, or I could say it's 1 minus 8 out of 23, which is another way to get that 15 out of 23. Example 11, one where the Venn diagram is needed but not given to us here. So it says in a class of 30 students, therefore the sample size is 30. 19 study physics, 17 study chemistry, and 15 study both of these subjects. First, it starts off asking us to make that Venn diagram. So let's take the information they gave us and put it into probability notation. So we start off with P, the event that they study physics, and C represents that they study chemistry. And we have to define events like that if they're not already defined for us. It's just like if you were doing an algebra problem and you have an X that represents the number of whatevers, you have to tell us that X represents the number of whatevers you're measuring there. So at first it says N, P intersection C. Okay, there's our notation there. P intersection C. And it says it's 15 because there are 15 who study both. Underneath that, we see the number of P and not C. P and not C. Well, that means that they are in physics, but they're not in chemistry. So how am I going to figure that out? I've already counted for 15 people in physics with the 15 already previously mentioned. There are 19 total people who study physics. So 19 minus 15 gives me 4 that are in the P event, but not in C event. And vice versa, you can do the same thing on the other side. The people that are not in physics, but they are in chemistry, 17 minus 15, and that gives me 2. And then the only thing that's left is to figure out how many people are not in either one of these subjects. And for that, I'm going to start with the sample size 30 minus 15 minus 4 minus 2 gives me 9 on the outside. So here's our Venn diagram. When you're making these Venn diagrams, you always start on the inside, the intersection, then work your way out. Make sure you're careful not to put out here that 19 value, because that 19, 15 of them already have been accounted for here in the middle, so there should only be 9 on that side. So now that we have that Venn diagram, now we have enough information to answer the question. Notice the notation for each one of these. Probability that they study both. Well, that's 15 people out of the 30, a half. Probability that they study at least one. That's any of these values that's in the circles. So 4 plus 15 plus 2 gives me 21 out of 30, or 7/10. Key but not C. Key but not C is going to be just these 4 people on the left side, 4 out of 30 or 2/15. Study exactly 1. Well, that means these 4 people count and these 2 people count, but these 15 in the middle, they don't count because they study both. And these 9, they don't count either because they don't study either. So it's just 4 plus 2 or 6 out of 30 or 1/5. And then finally, studies neither. That's just these guys left over. And that's just 9 out of 30 or 3/10. So that's it for this section here. Core book for Haese, section 10D. We talked about theoretical probability. We talked about how to represent them in different ways, help us find the different probabilities. And for the assignment for this, I'd like you guys to work on number 3 through 24 by 3s. I realize I neglected the page number there. I'll make sure to include that in the assignment that I post on Google Classroom. Hope you guys are doing well, and we'll get back together soon. Take care, guys.